Greetings everyone, welcome back to Calc 2. Time to start the second unit of Calculus 2, which is all about the things that we call sequences and series, specifically the infinite kinds of sequences and series. The main goal of this entire unit at the end is to give you a different perspective and a better understanding of the things that we call functions. There's a huge buildup, okay? And then the last couple of sections are like the main meat of what we're trying to get to. And we're about 8 or 9 sections away from that, okay? So for now, it's kind of like relearning a whole field or area from scratch. We're going to start with sequences, we're going to go to series, and there's all different kinds of those, and we have to talk about tests and proofs of things, and then we're going to build back with those back into functions. Okay, so for the next several videos, just need you to bear with me and just learn the skills that we throw out, and at the end you'll see that we are building these things back towards functions, which is mostly what calculus at this level studies. Okay, so to begin, sequences. Whenever you hear that word sequence, you think list of numbers, something that is sequential, right? Same root word. And you're not wrong, but we need a mathematical definition that's easy to describe and incorporate with the rest of the things that we study. So what a sequence is going to be defined as is a function whose domain is simply the non-negative integers, okay? So, in other words, we're not talking about continuous functions here. Eventually we'll build back into those, but a sequence, as you would normally think of it, right, is that list of numbers. In this case, 10, 12, 14, that's a sequence, okay? What you're going to be making this similar to is functions of something where you can only plug in whole numbers that are either positive or zero, right? Non-negative integers. And that's what this is right here. Z, the double line Z, is integers. I've labeled them as positive only. And then I've also incorporated 0, okay? So what's going to happen is you're going to have a letter A or B or whatever you want to name your sequence, and the little subscript is playing the same role as the variable in the parentheses for a function, okay? A sub n is the same idea as f of n, okay? But we're using the subscripts because not only is the n going to be an input for this thing like a function, but it also gives an ordering to the sequence itself, okay? So the n has 2 jobs. It is the input that gives you the particular value if you have your sequence in the functional format, but it also gives an ordering to the sequence of numbers, okay? So like in this example here, the 0th term, right? Typically the first term is either term 0 or term 1. A lot of times you'll see that we'll start at term 0, sort of like a physics problem like A naught, right? Or B naught, or function naught, or force naught, things like that. The subscript sometimes called naught in physics. But sub-0 is what we'll use here, okay? A lot of times I'll be starting with 0 as the beginning element. So in this case right here, a sub 0 is 10, a sub 1 is 12, a sub 2 is 14. And I have it in functional form as well. A sub n is 2n plus 10. So if I were to take the n value and plug it in, you would see that I would get that. And I could actually skip to anywhere else in the sequence that I wanted to, right? If I wanted to figure out what was the 25th element, right? A sub 24, because technically 0 was the first element. Stay with me. 25th element would be a sub 24, right? I would plug in 24. 2 times 24 would give me 48, right? Plus 10 would be 58. So then I could easily get to anywhere in there. But also I would know that that's a sub 24, right? Okay, so then some other terminology that we need to proceed throughout the whole chapter here. An arithmetic sequence. Notice it's not arithmetic, it's arithmetic with an E, right? It's a sequence that is formed by continuously adding a constant rate over and over and over again. Okay? So for example, -2, 5, 12, 19. Starting with -2, what you should notice is that at every item, I'm adding 7 to get to the next one. Right? And I could continue on in that sense. So an arithmetic sequence is something that's going to use addition. Right? So this is also an arithmetic sequence here. Next, geometric is one that you're going to be seeing a lot of. The geometric sequence basically is the same idea as the arithmetic one, but with multiplication of some ratio. Okay? So the way the geometric is really thought of is if you take any two terms and make a division or a ratio of them, that won't change from term to term. Okay? So in other words, I can use multiplication to get from one term to the next, or if I were to divide a term by the one previous, I would always get the same answer to that division. Okay? So here, between 2 and -2/3, notice that this was a multiplication of -1/3. And again, from -2/3 to 2/9, that also is a multiplication times -1/3. So on and so on and so on. Would give me a geometric sequence. If you ever watch the movies and they say, oh, it's growing at a geometric rate, and sometimes they'll even say an exponential rate. They're kind of the same thing, because to do continuous multiplication, right, you need exponents. So notice that's the generic setup for a geometric, has the n in an exponent, so that I know I can multiply the ratio that many times. Okay? And recursive. Recursive sequences are ones that the current term that you're on, that you want to calculate, calls on 1 or 2 or 3 or however many previous terms in the sequence. Okay? And not just a constant number. It's like, okay, I'm on term number 6, do this with term 5, and then you'll calculate term 6. Or I'm on term 8, do something with terms 7 and 6 and 5. Okay? That's what recursive means, something that calls on itself. The word recursive implies something that feeds or uses itself to create new elements. Okay? They have the same idea in computer programming. They have recursive algorithms that work by calling themselves. So here's an example right here. The Fibonacci sequence. All right, if you haven't heard of that one, definitely worth a look up. This one is something that is very linked to a lot of our natural phenomenon in the golden ratio. The Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13, is formed by starting with 1 and 1. And then for every term after that, you add together the two previous terms. So notice 1 plus 1 gives me 2. 1 plus 2 gives me 3. 2 plus 3 gives me 5. 3 plus 5 gives me 8. 5 plus 8 gives me 13. So on and so on. So to write this one recursively, you would say A sub n, in other words, the current term that you're on, n, is equal to the term just before it, n minus 1, plus the term before that, n minus 2. And that's how you would form this recursively. Okay? So a lot of this is just the terminology that will be thrown out whenever we're approaching these different kinds of sequences, right? And each one has its own different approach sometimes, depending on what you want to do with it, which is why you definitely want to be familiar with these categories. Okay? Now, another thing that's going to come up a lot in sequences and series, all for the rest of this unit, is factorial. If you've taken probability or combinatorics before, then you've probably seen factorial, okay? But let's go through it from the beginning. The idea of factorial is that I can take some value and multiply it by everything beneath it, counting down all the way to 1. And I say some value, I meant to say some integer. For basic factorial, you want n to be a whole number that is positive, a positive integer, okay? 0 factorial has to be specially defined. This is not calculated. You need to know that this is defined. It's more like it's a fact, accept it, move on. 0 factorial is 1. 1 factorial is also 1 because counting from 1 to 1 just gives you 1. Okay? 2 factorial is 2 times 1. Okay? 5 factorial is 5 times 4 times 3 times 2 times 1. So all you're doing is you're taking some positive integer and you're just going to count down to 1 and multiply everything from beginning to end, and that's what a factorial calculation is. There are lots of patterns in sequences and series that use this kind of buildup. So we need to know what this is. Negative 3 factorial, we don't have a definition for you for that right now. Square root of 2 factorial, even worse. That's not even a whole number. That's an irrational number. It's definitely not something I have an answer for you at this point. Sometime later, if you're interested in special functions, we use things such as the error and gamma functions and things like that to calculate off-the-wall weird things like this. These do have mathematical definitions, but it's not as simple as this. Okay? So for now, factorial is just listing a whole number down to 1, right? All the numbers in between and multiplying them together. That's what factorial is going to mean for you in this course. So here's some examples, right? 600 factorial divided by 597 factorial. If you were to punch this in your calculator, which, by the way, your calculator does have a factorial button. If you turn on the calculator, okay, and look, the PRB button, that is for probability. If you hit that, you'll notice you get a little menu, and in that menu, all the way to the right is an exclamation point, which is factorial. Okay? So, for example, if I wanted to compute 5 factorial, which, you shouldn't need a calculator for that, but anyway, it's 120, which is 5 times 4 times 3 times 2 times 1. Okay. If you were to punch 600 factorial divided by 597 factorial, you will get an error in your calculator. 600 factorial divided by 597 factorial. And that's because calculators are not smart. Calculators are only going to do what you tell them to do. And so the first thing it tries to do is calculate 600 factorial. That's not good. As you can see, 5 factorial is already in the hundreds, right? 10 factorial is going to be much, much larger than that. And you're only at 10 at that point. Okay? So factorial is something that grows very, very fast. However, humans, right, we can think outside of the calculator box, and we can perform this to such a point that I would eventually be able to put it in a calculator. Like this. Remember, something factorial is just a listing of all the numbers beneath. So if I do n times n minus 1 factorial, okay, or I can do that as many steps as I want and then just represent a tail. This is what I mean. 600 factorial, I don't want to list out 600 numbers here, right? Or 601 numbers. I would only want to list the important ones. So 600, 599, 598, and then 597 factorial, right? You see the 597 factorial is also in the denominator, which means I can reduce the 597 factorials. And all I'm left with is 600 times 599 times 598. And then that is something you can put in a calculator, or you can do by hand, either way, whichever one you want to use to simplify it, okay? Without having to do all of those other multiplications. 7 factorial divided by 3 factorial times 4 factorial, right? So obviously in the numerator I would do 7 times 6 times 5 times 4 factorial, and in the denominator I would do 3 times 2 times 1 times 4 factorial. I wrote out the 3 factorial and I wrote out some of the 7 factorial because I noticed I'll be able to eliminate the 4 factorials. And then 3 times 2 is also 6, right? So I can wipe that out. And then all I'm left with is 7 times 5. Okay? So this is the kind of logic that you need to have with factorials. Where's the biggest chunk that I can wipe out first? And then generically, n minus 2 factorial over n factorial. That's the kind of thing you're going to see in sequences and later on in series as well, because we have things that are represented generically with n's and i's and k's, whatever variable you're using to count your sequence. So in this case right here, n minus 2 factorial over n factorial, I would write out like this. I would keep the n minus 2 factorial because remember, n minus 2 is smaller than n. So in the bottom, I'll write n times n minus 1 times n minus 2 factorial, so that I can reduce the n minus 2 factorials, leaving me with just 1 over n times n minus 1. And then that would be considered simplified. One important thing that you'll want to be able to do with a sequence is be able to take some sort of listing of the sequence and convert it into the functional form, the nth term. Okay? If you know what the nth term calculation is, then you can figure out what any given term is. And also, in a little bit, we're going to talk about how the nth term can be used to look at the very end of an infinite sequence. And I know that's sort of an oxymoron type of thing. That's, you know, like double talk, like how can you have an end to an infinite sequence, right? And we're going to talk about limits with that. Okay, so we need to be able to have something in terms of a generic nth term, which is going to be these functional forms. Okay, so here are some examples of ways that some sequences can be converted into a generic nth term. Let's start with this first one here. 1, negative 4/3, 16/5, and negative 64/7. Okay, so the first thing I'm noticing is that it's what we call alternating. Alternating means that it's changing signs from positive to negative constantly. Okay? Alternating. And that can happen with any type of sequence, that it can be what we call alternating. There's normal alternating, positive, negative, or negative, positive, whatever. And then there's skip alternating, where you go positive, negative, positive, negative, or you can do things like positive, negative, positive, negative. Yeah, there's all kinds of patterns like that. They're still considered a type of alternating. Okay, typically the alternating that we run into are just the ordinary alternating where every other is positive or negative, like that. Okay, so for things that when you notice they're alternating like that, you can ignore the alternating because we can actually do that as a separate multiplied piece for the nth term there. Okay, so I'm going to worry about the alternating in a minute. And what I'm going to focus on is any pattern in the numbers that might involve addition, subtraction, exponents, things like that. Okay, so the first thing I notice is that 1 is not the same structure as everything else because 1's a whole number. So I'm going to start by thinking of 1 as a fraction, right? 1 over 1. And then for negative 4 over 3, okay, the only other pattern I'm seeing maybe is the pattern with the 4, 16, and 64. Those are all powers of 4. So I'm seeing 4 to the 1 over 3, 4 to the 2 over 5, 4 to the 3 over 7. And then, of course, the denominators, I'm also seeing an an odd number pattern, 1, 3, 5, 7. So I've definitely got that kind of pattern for the denominator locked down. How does the 1 in the numerator here fit in with the powers of 4? Well, easy. 4 to the 0 is also 1. So this could easily be 4 to the 0 over 1, 4 to the 1 over 3, 4 to the 2 over 5, and there we have it. We've got a pattern going on here, okay? So then how do I write this in a generic nth term type of setup? Well, obviously, I would have something like a sub n is equal to, and remember our first term, a0, right? This right here should be a0 or a1. If I've got this 0 though in this first term here, I'm going to try and use 0 if I can. Okay, so a sub n, notice it counts 0, 1, 2, 3. This is going to be a1, this is going to be a2, this is going to be a3. And notice the exponents match the subscripts there. So a sub n is going to be 4 to the n in the numerator. And then I just need a way of describing an odd number sequence. Okay, so this is something that you need to know. 2n plus 1 or 2n minus 1. Okay, as a whole, something where it's 2n either plus 1 or minus 1 is like a guaranteed odd number. And I picked plus 1 because when n is 0, I get 1, right? Notice when n is 1, I get 3. When n is 2, I get 5. So just keep this in mind. Something that's 2n plus 1 or 2n minus 1 is always going to be a sequence of odd numbers. The other way around, if you want to do a sequence of even numbers, you just put 2n. So that would go 2, 4, 6, or 0, 2, 4, 6, either way. Okay? So 2n plus 1 or 2n minus 1 is something good to keep in the back of your mind for a sequence of odd numbers. Okay? Now we haven't accommodated the alternating negatives yet, because notice right now everything I plug in is going to give a positive. Okay? Alternating is easy to accommodate. You simply multiply the terms by negative 1 to the n or n plus 1. The n or n plus 1 in this exponent is going to determine which every other term grouping is negative and positive. Okay, so look at the first one. I want my first term to be positive, so that's a 0. If I plug in 0, negative 1 to the 0 is just 1. So that works out. Check it again, a1. If I plug in 1 for n, negative 1 to the 1 power is negative 1, which would cause it to be negative, and that's exactly what I want. So here is my generic nth term for this sequence here. All right? Now, what about recursive algorithms? The next few here I'm going to talk about are recursive algorithms, because you can see what I have given you is a beginning value and then some sort of way to associate a current value to a previous value. Okay, these next two right here are what we call the geometric. And I know this because of the way that we were talking last time, if you remember. The way that we were talking last time about geometric Remember when we were saying that it had to do with multiplication or ratios? Well, notice ratio of the two terms is always the same number, right? So this is a previous term, n minus 1, divided by the current term to be 3, okay? And this is another way of saying the next term, a n plus 1, is equal to some value times the current term, a n. So again, those are both geometric because it has to do with multiplication of a constant. Okay? Every term is going to be the next one down. So this is what I do. Whenever you have a recursive algorithm, no matter if it's geometric or not, it's best to go ahead and calculate a few terms by just plugging in the values, and then you'll have a list to work with, like what I've got there. Okay? So a sub 0 is 2, right? This right here is telling me if I multiply both sides by an, notice that I'll get an minus 1 is equal to 3 times an. Okay? That's not what I need. Okay? What I need is to then divide both sides by 3 so that I have an by itself. Okay? So then I'll have, I'll move this way. An minus 1 divided by 3 is equal to an. Okay, so the reason why you want it that way is because the term with the more recent value should be the thing that you're calculating. Okay, so a sub n minus 1, if I let that be 0, then a sub n would be a1. Okay, this is telling me that a0 divided by 3 is equal to a1. Think about it. If n is 1, then 1 minus 1 is 0, right? So on and so on. So that also means that a1 over 3 is equal to a2, right? Because if this is 2, 2 minus 1 is 1. And this will just continue on recursively. Every time I want to calculate a term, I'll just take the 1 before it and divide by 3. So a0 is 2, right? That means a1 is 2/3. Then I'll take that one and divide by 3 again. A2 is 2/9. A3 would then be 2/27, and so on and so on. All right? So then that means I can make my generic term like this. Notice every time I go from one term to the next term, I'm multiplying times 1/3, right? Times 1/3. So my generic right here, a sub n, is going to be the number 2 that I start with times 1/3. And then how many times I multiply the 1/3 is going to depend on which term I'm on. So I'll raise that to the nth power. And it's like I was showing you in the previous scene. Anything geometric is going to have a constant number raised to your variable power, because that tells you how many times you're going to multiply that object. Okay? So I'm starting with 2, and then if that's 0, remember anything to the 0 power is 1, 2 times 1. So this is already ready. Okay? This is the generic term for that particular geometric sequence. Okay? So remember that format. Geometrics always have this kind of structure here. Notice I can see right away that this one is geometric also. But don't let the subscripts fool you. This time an is the lower because this says an plus 1. So this is actually already set up and ready to go. If I have some term that I want, I simply multiply negative 1/4 times the current one. That's next. This is current. Okay? So here I go. I'm going to start with 5, right? So a1, right, is going to be a0 times negative 1/4. So 5 times negative 1/4. Then a2 would be that same thing, right? a1 times negative 1/4. Okay? A3 would be 5 times negative 1/4 times negative 1/4. This is A2 right here times negative 1/4 would give me A3. So AN, the generic term, is going to be 5 times negative 1/4 to the n. Notice again, that's that geometric setup where I have a constant term multiplied by itself an n number of times, so I use an exponent, and then my beginning term is just something that's multiplied in the front. Okay? Also note that this would have been an alternating series, or an alternating sequence, not series, we're not doing series. It's an alternating sequence, because A0 is positive, A1 would have been negative, here double negative is positive, triple negative is negative. So this would be an alternating sequence also. The negative 1 to the n, you see, is built in to this multiplication already, the same way I had it artificially up there. Okay, so here's something that's arithmetic. I have the new term n is based on the previous term n minus 1, and I'm just going to be adding 3 every time. Okay, so that means if A0 is 7, then A1 is going to be 7 plus 3, 10. Then A2 is going to be the previous term, 10 plus 3, so 13. And so on and so on and so on. So then my AN is going to be 7 plus, notice I'm just adding 3 every time, so it's plus 3 times n. Notice those are linear type of functions, right? Something with a constant rate of increase in this case. Here's an offshoot of arithmetic. It's not exactly arithmetic because it's not a constant rate of increase. Notice I'm adding n. This one just a little bit different than the one before, but enough that it's probably worth mentioning. This is going to talk about something from Calc 1 that you've seen before. Let's talk about this one for a second. I have a sub 0 is 0. So then A1 is going to be the 0, right? Plus n. Here n is 1. And then A2 is going to be the 1, the previous one, right? Plus n. So I get 3. So then A3 is going to be 3 plus 3, which is 6. Right? What about A4? It's going to be the previous one, 6 plus 4, which is 10. So notice every time I go up 1, right, I'm adding the new number, right? I added 3, I added 2, I added 1. So if I have something like A sub n, then what I'm really doing is adding everything from 0 all the way up to n. Well, you already know a formula for that, right? From when we were talking about the basics of integration, if I want to add up a list of numbers starting with 1, the 0 doesn't matter here because it doesn't add anything. We had a formula for that. In this case, a sub n is going to be n times n plus 1 divided by 2. Because you had a formula for that one. You need to go back to the beginnings of Riemann integration and look for that. I have it in my Calc 1 series, right? That's how you add up all of the integers from 1 to some number n. N times n plus 1 divided by 2. Okay, my sequence can have variables in it. Sure. In fact, this is eventually what we want to work up to, okay? Something called a power series is what this is akin to. This is the idea eventually that we're going to have variables in the sequences and series also, okay? Notice I have defined x to be something that is real. That's not the same as the n's that we're using for these other things where n is an integer, okay? X is an actual real variable that I'll be having as some sort of functional variable. But that's okay. I can still use n's on top of the x's. Notice x is just a common term in each one. Okay? So let's go back to what we were doing over here with patterns. Notice I have the x pattern. X to the 1, x to the 2, x to the 3, x to the 4, x to the 5. So that's going to be an easy thing to settle, right? 1 can be x to the 0, right? So I'll just rewrite this with the idea that this is x to the 0, x to the 1, x to the 2, x to the 3, so on and so on, right? Okay, and then we'll worry about the denominators in a second. But notice a sub n is going to be x to the n in the numerator, right? That's the easy pattern we see. Now, the denominator on the 1 here is 1. The denominator on the x here is also 1, 2. Instead of 6, I'm going to write this as 2 times 3. I'm looking for patterns here, so I'm going to start breaking these things down. The denominator on the next one, 24, is 2 times 3 times 2 times 2, or just 4. Are you seeing a pattern yet? This is x to the 5 over 2 times 3 times 4 times 5. The only thing we're missing is the 1 times on each one. And I'm hoping that this is starting to strike a bell from what we just talked about in the last thing. These are factorials, right? 120 is 5 factorial. 24 is 4 factorial. 6 is 3 factorial. 2 is 2 factorial, because that's 2 times 1. 1 is 1 factorial. And 1 is also 0 factorial. So I can actually just put n factorial right here. Double check this. Is this first term a sub 0? Right? If I plug in 0, I get x to the 0, which is 1, and 0 factorial, which is 1. So I'll get 1. A sub 1, x to the 1 over 1 factorial, which is x. Right? X squared over 2 factorial. X cubed over 3 factorial. Right? So it fits. Okay. For this next one, what you need to start considering is that sometimes fractions get reduced. So I want to start writing out this pattern here. I'm noticing 6, 7, 4, 3, 5, 11. Now wait a minute. What if I did 6, 7, 8, 9, 10, 11? See, that would fit, wouldn't it? But then where's the 8, 9, and 10? They probably got reduced. So if I do 6, 7, 8, 9, 10, 11, that's a counting pattern, and it looks like it goes with the numerators. But look, if this is 4, that would be the same as 8 over 2, wouldn't it? And then 3 over 2 should have been 9 over 6. And then 5 to be 10 would be 10 over 24. And then this is 11 over 120. And let's continue the structure here. This would be 7 over 1 and 6 over 1. I'm hoping that you're noticing a very similar pattern to up here, right? 1, 1, 2, 6, 24, 120. Those are my factorial numbers, right? I just had to unreduce to see them. And these are just counting 6, 7, 8, 9, 10, 11. Except instead of starting with 0, they start with 6. Okay? Well, that's easy to fix. Obviously, we can see the factorial denominator, right? So n factorial for my denominator. The numerator, if I start with 0, right? If this is a sub 0 here and this is a sub 1, then I need to find a way for 0 to turn into 6, 1 to turn into 7. And that's easy. I'll just use addition. N plus 6, right? 0 plus 6 is 6. 1 plus 6 is 7. 2 plus 6 is 8. 3 plus 6 is 9. So this is A2, A3, A4, A5. And it fits that pattern. I have n plus 6 over n factorial. Okay, so let's continue. More patterns, right? I see 9, 27, wait a minute, 1. That doesn't seem to fit, right? So 1 is definitely something where I need to mess with the structure and probably turn it into a fraction. Then I see 243 and 729. Okay, well, I'm hoping you're already seeing the numerator pattern, because that's just a pattern of powers, right? 9 is 3 squared, 27 is 3 cubed, 243 is 3 to the 5th, 729, 3 to the 6th. Well, what's missing, right? The 1 would have to be 3 to the 4th, wouldn't it? Sure enough. And if it's 1, then it would have to be over itself, wouldn't it? 3 to the 4th. 16, however, is not a power of 3. And then, of course, if this is going to be a fraction, right, we're going to stick with that. But wait a minute, 256 and 625. I'm hoping those numbers ring a bell to you too. This is 3 to the 4th here. 256, that's 4 to the 4th. 625, that's 5 to the 4th. Let's go back. Is 16, 5, 4, 3, 2 to the 4th? Sure is. And then this is 3 squared, 9 is over 1. Would that be 1 to the 4th? Sure. Notice I don't have technically a 0th term here. If you want, you can actually call this one A1 if you wanted to, and A2. It's completely okay to do that. Notice if I do that, my denominators match my call numbers here, right? A3, so on and so forth. So for A sub n, I'm noticing that I have n to the 4th in the denominator there. Okay, what about the numerators? Well, if this is A1, I have 3 to the 2. A2, I have 3 to the 3. So it's going to be 3 to something up here, right? I need an exponent. But it looks like the exponents are always 1 ahead of the subscript I picked. So I'll just put 3 to the n plus 1 here. And let's check it, right? If I plug in 1, I get 3 to the 1 plus 1, which is 2. And I get 1 to the 4th, so I'll get 9. That works. Check another one, like 4. If I plug in 4, I'll have 3 to the 4 plus 1, which is 3 to the 5th, 243. And 4 to the 4th is 256. So it works. This is my generic nth term here. Okay, so it's all about writing out these patterns, guys. Okay, so 1 3/5, 9 25ths, 27 over 125, 81 over 625. Okay, I'm hoping that you're seeing the pattern here, right? The top are powers of 3. The bottom are powers of 5. And what about 1? Anything to the 0 is 1, right? So I could say that this is 3/5 to the 0, 3/5 to the 1, 3/5 to the 2, right? So on and so on. Because 3 squared, 5 squared, 3 to the 3rd, 5 to the 3rd. Okay? And this is actually a geometric series again. You don't have to use little a. I can use any letter I want. B sub n, if I wanted to, would be 3/5 to the n here. And it's a geometric sequence. Okay, one more. Negative 3/7, 9 25ths, negative 27 over 79, 81 over 241, negative 243 over 727. This one's not as obvious. I'm hoping you're seeing the alternating at first, though. Remember, that's something I can fix at the end. It is alternating. Okay. Powers of 3 on the top. 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4. Okay, so we're seeing that one. Let's write that down. All right, I have 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4, 3 to the 5, and that's my numerators. Right? Okay, now here's another thing that you can sometimes notice. Sometimes the patterns in these things follow the same things, but they're off just by an addition or subtraction. So I'm hoping that you'll see this. 9 minus 2 is 7. Do you see that? 27 minus 2 is 25. 81 minus 2 is 79. And 243 minus 2 is 241. Now, of course, we're not working backwards in the sequence. I'm just showing you that these numbers are always 2 off of the next numerator. The next numerator is just another power of 3. So notice this denominator right here is just 3 squared minus 2, right? It's this numerator, but minus 2. Next, this one is going to be 3 cubed minus 2, right? Because it's that numerator. This is going to be 3 to the 4th minus 2. See the pattern evolving? So then my generic term here, a sub n, is going to be, I have 3 to the n, as long as I labeled this one as a 1 this time. Okay? A 1. Not a 0, right? Because if I did a 0, it would be something different. And then in the denominator, notice I have to go up a power, right? If this is n, right? 1 and 1, and this is a2, so 2 with 2. I'm always a higher power 1 by 1 in the denominator. So this is going to be 3 with an n plus 1 exponent. And then every time I'm subtracting 2 away from that total in the denominator right there. Okay? And then last thing, don't forget this one was alternating in sign. But I need the first one to be negative, right? So let's be careful here. I'm going to multiply this whole thing times negative 1. And I'm going to start with n, and I'm going to check it, okay? The other option would be to put n plus 1. Sometimes you can do n, sometimes you can do n plus 1, okay? With n, if this is 1 and I plug in 1, negative 1 to the 1 is negative, which it should be. So this is actually good. If I'd have put n plus 1 here, then the negatives would have shifted to the second one, all the even terms. Okay? So just keep that in mind, that doing either n or n plus 1 can move the negatives to the other alternating group. Something that's quite important to be able to do is to take the limit of a sequence. And typically limit is a rather broad term, but when you say the limit of a sequence, typically what is implied is what's going to happen to the sequence as the counting variable is allowed to go off to infinity unbounded. Okay, in our case n, as n goes to infinity. Okay, so one way that you can think of this is to think of it like a function, and like any function that you let go to infinity, right? You have some functions that are bounded and some functions that are not, and so if you are going to have a limit as n goes to infinity, right? Say L, then for the most of the time, that would be the same thing as taking the limit of some function of n and getting a value of L. Now I said most of the time, there are a few exceptions, okay? So we do actually have the correct language for doing limits, just like you would do a limit of a normal function. The difference is, of course, with sequences, their domain is not continuous like that of the functions that we typically study. So I can't just take the limit anywhere I want within a sequence. Really, the only limit that makes any sense is the one where we get the pattern of numbers as n goes to infinity. Okay? Now, of course, you should also realize that that implies that I will not be taking any derivatives of sequences. That much is true. We can't have any continuity at any given single point. Therefore, we will not be doing any derivatives at points like that. Later on, we'll talk about doing derivatives of other variables, not the counting variable. Okay? We won't be doing any derivatives involving n, because n is not defined on a continuous interval of any kind. Okay? The limits that we're going to be interested in as n goes to infinity are going to also give us important information, and we'll discuss convergence and divergence in a moment. But just being able to take the limit, okay? So like I said, most of the time you can think of this as the sequence is some sort of function, and that's what we were just discussing about turning the sequences into, some generic nth term function form, okay? And then we'll be taking the limit of those things just as if they were a normal continuous function, and all of the limit stuff that you remember still applies, but you have to be careful, because remember, n is not continuous, and I won't be doing derivatives with n, which means I cannot directly apply L'Hopital's rule. Let's go through a few examples of some simple limits first, and then in the next scene we'll talk about how we can still use L'Hopital's rule by using function bridging, right? Okay, so the language, of course, for limits is the same. For every epsilon that I could think of, there should exist some m such that when n is greater than m, the sequence draws close to the value of L. What that means is if you actually have a limit equaling some value L. Now, of course, if your limit is unbounded, if your limit is going to infinity or negative infinity as an output value, then of course you won't be able to find an m for every epsilon such that a is approaching some value. A is just going to be unbounded. Okay? So the whole idea here is if your limit does actually equal some finite number, then for every epsilon, you should be able to find, some cap, in other words, some m, some number of terms, such that once you pass that number of terms, you're always going to be close to the value L. That's basically what this language is saying. Okay? And then, of course, there's the idea that the limits are the same depending on the variables, and they're not. Okay? Notice with a continuous function, 1 over x, you're actually looking at a connected continuous curve. Okay? The limit still gives an output of 0 as x goes to infinity. Okay? Just like it does with the n here, as n increases, right? But the difference is with the n, we're only looking at specified locations, right? N equals 1, n equals 2, n equals 3, n equals 4, right? So A1 has this value, A2 has this value, A3 has that value on the y-axis, okay? So that's what the sequence is actually going to look like if you were to graph one, and we'll take a look at a few in GeoGebra as well. All right, so keep in mind that this is what we're actually doing, and this is what you might be thinking of when you're performing these limits, and you just have to be careful that you're using the proper rules and everything. Okay, so let's do some of these examples here. Limit as n goes to infinity of 2 to the n plus 5 to the n over 4 to the n. Now, of course, in its current condition, this is not exactly a very nice thing to take a limit of. Instead, I'm going to break it up. This is going to be the limit as n goes to infinity of 2 to the n over 4 to the n plus 5 to the n over 4 to the n, like so. And then I can simplify both of these somewhat to the limit as n goes to infinity of 1/2 to the n plus 5/4 to the n. Okay, so then from here, I'm going to apply a lot of my old school ideas of limits, the old ways that we got used to performing limits, because most of it is the same, right? I'm still letting n go to infinity, which means I am going to be multiplying 1/2 by itself approaching an infinite number of times, right? And as with anything exponential, if you're letting the exponent go to infinity, it depends on the base object. If the base object is less than 1 in size, then the limit of that is going to go to 0. Because I'm multiplying by 1/2 over and over and over and over and over again, right? 1/2, 1/4, 1/8, 1/16. It's going to continue to get smaller and smaller, very similar to this. However, 5/4 is bigger than 1. You keep multiplying by that, it's going to keep getting larger and larger. So as n goes to infinity, this piece right here is going to infinity. And I have a very straightforward, that limit is 0, that limit is going unbounded. So the answer to this limit is going to be infinity. Okay? So just keep in mind whenever you're doing the limits of these things, it's going to be very similar to the limits that you've done before that dealt with infinite boundaries on these things, okay? For the next one, limit as n goes to infinity of ln of n plus 3 over n squared minus 5. This is going to be equal to, let me go ahead and separate this. This is going to be equal to the ln of the limit as n goes to infinity of n plus 3 over n squared minus 5. Right? Now, varying different degrees of different rules that you want to apply here. One of the things you could do is, divide everything by n if you want or whatever. But most of the time, you remember just those quick little rules that have to do with having infinities in a rational function, right? In a rational function, if the denominator has a higher power, then this limit is going to go to 0, right? That's exactly what's going to happen here. This limit is going to go to 0. But here's the problem. I can't do the ln of 0. So here's what I'm going to do. I'm going to rewrite this now as the limit as a approaches 0 from the right of the ln of a. Just think about that for a second. As n goes to infinity, right, this value altogether goes to 0 from the positive side, right? This is going to give nothing but positive values, and it's going to come down to that, okay, as n goes to infinity. So as a approaches 0 from the positive side, from the right, and I'm going to be doing the ln of that. Okay, so remember your graph of logarithms, right? As you approach 0 from the right, the ln goes down to negative infinity. So I'm actually going to get that as my answer here. Seems justified on a couple of these things, right? We have an infinite list of numbers, so it makes sense sometimes to us that the numbers would go off to an unbounded limit. That's not always true, okay? Some of the limits that we do actually do what we call converge on a actual finite value. Okay, these are just some examples of the different setups that you might run into. Here's one that sort of seems off the wall and doesn't exactly fit into the total definition here. With this one, you need to do a calculation first. Anytime you see cosine of pi n, it's going to be different than if it were cosine of pi x, right? Where x is a continuous variable, n is only integer numbers, right? So remember now, all I'm going to be doing is, as n goes on and on and on, I'll have cosine of 0, cosine of pi, that's 1 times, right? Cosine of 2 pi, cosine of 3 pi, so on and so on and so on, right? The n is just going to count by whole numbers. Well, with cosine, every time you hit a pi, you get a value of 1 or negative 1, right? Cosine of 0 is 1, cosine of pi is negative 1, cosine of 2 pi is 1, cosine of 3 pi is negative 1. So it seems to me like I could actually rewrite this limit like this. This would be the limit as n goes to infinity of 5 plus -1, and it would be, say, to the n power-ish, right? Depending on which way you want to look at it. When n is 0, right, I would get 1. I still do. And then when n is 1, I get -1. So let's take a look at what's happening here. As I plug in every single value of n, right, I either get 5 plus -1 or 5 plus 1. So I either get 6 or I get 4. I get 6 every time n is even. And I get 4 every time n is odd. Well, is infinity even or odd? And then which one of these things do you think it would actually rest on if I could get to infinity? Trick question. It can't rest on either one, right? 6, 4, 6, 4, 6, 4. So the limit here is more of just a eye candy for what it actually wants you to do. It wants you to take a look at this sequence and determine what you think would happen at the quote-unquote end of the list. Even though it's an infinite, it doesn't have an end, I know. What do you think would happen? Well, it would keep going forever, right? 6, 4, 6, 4, 6, 4, 6, 4. It would never be able to stop on either one, because every time you'd have 6, well, you can go one more step and get to 4, then you can go one more step and get to 6. It's never ending. So this right here is one of those types of sequences that simply doesn't have a limit, right? It's not infinity, it's not negative infinity. The limit itself is undefined. Because it never settles on any particular value, and it doesn't, increase without bound either. It doesn't settle on infinity either. It never actually stops. Okay? Something similar, anytime you have something periodic like a tangent of n, right? If you look at the graph of tangent, it keeps going up and then back down and then up and then back down and then up, and then it repeats over and over and over and over and over again. So where actually does this thing land? It'll stop over here, then it'll be down here, then it'll be up there, then it'll be randomly way down here, then way up here, then it might get closer again. It'll keep doing random spots, because notice I don't even have a pi in there or anything. The numbers n are going to be measured in radians, and each one is going to land on a random, well, not random, but it can be calculated, but it's going to seem random the way the dots are just going to appear all over different curve after curve after curve of the tangent swooshes. Okay? So this one can't settle on anything either. Anytime you have a sine or a cosine or a tangent like this, okay, it's very easy to see that just this plain thing by itself can't settle on it. It's also undefined. Okay, now let's actually work one here that does actually converge to a value. I'm hoping you recognize this particular sequence. It's one of the ones we formed earlier, right? So the limit as n goes to infinity of n plus 6 over n factorial. Right? So it's kind of like asking, hey, with that list that we were looking at earlier, what would the end of that list look like? Right? Okay, fine. So on this one, I can't easily do a limit with n factorial. N factorial is one of those things that we've never really experienced with limits before, and also it only is working on integers. I can't like flip the factorial back over to a continuous function and think about, hey, what would happen, and then try to bring that idea back. It's not going to work. So dealing with factorial is going to feel a little different. You're going to have to try and find a way to let it mix and mingle and interact and break apart as best as you can. Okay? So here's what I'm going to do with this one. I'm going to break it into two fractions. The limit as n goes to infinity of n over n factorial plus 6 over n factorial. N over n factorial can reduce, so I have the limit as n goes to infinity of 1 over n minus 1 factorial. think about that one for a second, right? Because remember, n factorial is the same thing as n times n minus 1 times n minus 2, da 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 da, all the way down to 1, right? But if I cancel out, if I eliminate these n's, I'm just left with n minus 1 all the way down to 1, which is leaving me with n minus 1 factorial. Okay? Well, now, no matter which way you look at it, you can tell right away what the answer to these limits are, right? This is going to be 1 over something that's increasing without bound. 1 over just n, right? Over here, 1 over n goes to 0. This is going to get bigger even faster because there's more things to multiply on the bottom, but the top stays as a 1. So that limit goes to 0. Same idea here. This is just 6 times 0. Okay? So overall, this whole limit is going to go to 0. All right? There are limits of all different variety here, just like before. There are limits that actually converge, we call it, on a particular value. And then there are some that are unbounded in certain ways. And then there will also be limits that are just flat out undefined because of the way the patterns of these sequences work. Let's continue to talk about this, and let's also take a look at what some of these sequences look like in GeoGebra. So let's take a look at what these sequences look like graphically. As you can see, I have them plugged in as functions. These are what the functions would look like if you were just graphing the continuous curve. But remember, with the sequences, we are graphing only the whole number inputs. So we end up with just these points. The actual sequence would look like this. And if you recall, this particular sequence, 2 to the n plus 5 to the n over 4 to the n, was having a limit of positive infinity, and you can see that in the dots there, in the points. They are increasing without bound at all moments there. And it doesn't take very long. As you can see, I'm only up to, like, n is in the 20s right here, and it's still increasing very largely. Okay, next, let's take a look at the g function. ln of x plus 3 over x squared minus 5. And again, this is what the function looks like. You can see that it drops here. And if I shrink this up so that you can see the whole scale here, let's even shrink it, the n-axis here. You can see that this function by itself decreases without bound, and the sequence is going to do the same thing. You can see the sequence, these are the individual dots, and the sequence is doing the same thing that the curve is doing. It's decreasing without boundary, very slowly, but without boundary, to negative infinity. Okay, now an interesting one to look at next was tangent. Let's get a look at what tangent looks like normally. So, you know, 1, 2, 3, or 4 of these swooshes here, that's what we're used to seeing for tangent. And if I make the sequence calculate for this particular one, we can see where the dots are here. And as we said before, they seem sort of random. Of course, these are not random, they are calculated, but look how the dots are not totally evenly spaced. They're in different locations in each of the different swooshes here. So there's no one pattern to how these things are going to look. If I take away the graph and we just focus on the dots themselves. So then if I expand this out, you can see it looks kind of like they're increasing away, but shrinking this up, it's not that they're moving away from anything. you can see that the dots just tend to just spread all over the place. So there's really no one number that this thing could limit itself towards for tangent. Okay, next let's take a look at the 5 plus cosine of pi x, or in the sequence it would be cosine pi n. The function itself looks like this, and this is what you'd expect. It's a cosine function, right? It's just a sinusoid bouncing back and forth between 6 and 4. But remember, that's the continuous variable. The sequence is only going to use whole numbers for its input. So you're only going to get the peaks and the troughs there, as you can see. That's the actual sequence that we were talking about, which is why we don't get a limiting value. It constantly bounces between 6 and 4. And lastly, we're going to talk about the x plus 6 over x factorial. Function q there. As you can see, there is a curve for this. GeoGebra knows enough advanced math to be able to give you a nice smooth curve, even on the in-between values, non-integer. But we're only interested in the integer values. And as you can see, this thing very, very quickly approaches 0, its limiting value for this sequence here. It doesn't take very long for it to just ride the line there. So as I mentioned before, you can use L'Hopital's rule with these. We just have to be a little bit more careful with the terminology. Since technically I cannot take a derivative of the variable n. N in these cases is defined as a discretely distributed variable. It can only be the whole numbers. So there's technically not a d over dn defined here. Okay? But the way we are able to bridge a limit of n over to a limit of something with x as a continuous variable, as long as you can bridge over to a continuous function, then you can still apply L'Hopital's rule, because the limit of the sequence is going to be the same as the limit of the function. And that's simply because whenever you have, say, something that's going to approach an asymptote right here, right? If I have some continuous function f of x that's going to approach that asymptote, if I'm going to have some f sub n, right, or f of n, all that would be is the difference would be, it would just be hitting the curve at certain points. But at infinity, they're going to be approaching the same asymptote. Okay? So especially for all of the type of sequences that we're going to be looking at here, as long as you can, shift over to a continuous function, then you should be able to use L'Hopital's rule the same way we would before. The only exceptions, of course, we saw a minute ago is with factorial. Factorial we typically don't allocate with continuous functions, and that's because the factorial only works on integers, and to put it on a continuous interval would take some more advanced mathematics with special functions. All right, so things with factorials, you're going to have to figure out some other way to approach them. But for things like these, I can easily just switch over and the limit will stay the same. So for example, what I'm going to do here is I'm going to say that this limit is equal to the limit as x goes to infinity of x squared over 3 to the x. So I'm taking my sequence nth term generic function and turning it into just a normal continuous function of something like x. And it doesn't have to be x, you can use y, z, whatever. Okay? Just so that you know, n is the variable that's defined only on the non-negative integers, and x is the normal continuous variable defined on all real numbers that we're used to dealing with. Okay? Even when you switch these over, okay, even when you do that, you'll see in later chapters here, I still restrict x to being non-negative only, because I really don't care about that portion of the graph, because my sequence is not going to exist over there anyway. All right, so even if I switch to something that's continuous like this, I'm still only considering the non-negative half of the grid. All right, so this limit right here, I would need to use L'Hopital's rule because I have infinity over infinity. Therefore, I take the derivative of the top and bottom independently. So I have 2x over 3 to the x times ln of 3. Next, I still have infinity over infinity. So I do it again, L'Hopital's rule, limit as x goes to infinity of 2 over 3 to the x times the ln of 3 squared. And now I can notice that I have 2 over infinity pattern-wise, basically, which this is going to go to 0. Okay? So I am able to say that the limit as n goes to infinity of this sequence is actually still equal to 0. All right, so what about the nth root of n? This kind of thing is going to come up a lot also later when we're doing some of our series tests. We have something called the root test. We have sequences of things with radicals, okay? And even though this doesn't have a denominator, the fact that the radical can increase in root number allows this thing to still have the ability to not blow up and be unbounded all the time. So let's see what happens with this one. I'm going to convert it, limit as x goes to infinity of the xth root of x, which I would be tempted to rewrite limit as x goes to infinity of x to the 1 over x power. And so what I have is the indeterminate form infinity to the 0 power. And remember, those indeterminate forms are able to be used with L'Hopital's rule after some manipulation has occurred, right? So then I'm just going to say that this is equal to some value L, if you remember. The technique on this one is I let it be equal to some value L, and then I put a logarithm on both sides, okay? So I've got the limit as x goes to infinity of the ln of x to the 1 over x is equal to the ln of L. And then, of course, inside of a logarithm, I'm able to bring exponents out. So what I have is the limit as x approaches infinity of 1 over x times ln of x is equal to ln of L. And instead of, I've multiplied the 1 over x out front, but an easier way to accommodate this would be just to go ahead and multiply it through as just ln x over x. Now I've got an infinity over infinity situation, right? That as x goes to infinity, so does the ln value, and of course x is going to infinity. So I can use L'Hopital's rule here to show me that the limit as x goes to infinity, derivative of ln x is 1 over x, derivative of x is 1, and this is equal to the ln of L. Okay, so as x goes to infinity, this piece is going to go to 0, right? 0 divided by 1 is 0, is equal to the ln of L. So then, of course, I raise my base e on both sides, and I get that 1 is equal to L. And since 1 is equal to L, and L is equal to all of these, then I can confidently say that the limit as n goes to infinity of the nth root of n is also 1. Okay? So we can still use L'Hopital's rule. You just got to be careful and make sure that it's perfectly legal to turn it into something continuous. Don't just assume that you can do a derivative or L'Hopital's rule with the ends, because those technically are not continuous and cannot be treated in that way. All right, so when you're working one of these problems, make sure that you designate the fact that you have switched to something continuous, especially if your teacher is someone who likes to see those details and make sure that they can understand that you understand those types of things. Don't forget good old squeeze theorem when it comes to limits. Sometimes you just need a different approach to some of these objects that aren't as obvious with limits that go to infinity. In the cases of these two right here, squeeze theorem is especially helpful because of the nature or the structure of the object. On the a sub n here, having that sign of n in there really kind of throws off your pattern, okay? Visually, you can kind of tell that it should go to 0 because sign doesn't get very large, but n does. But the whole point is showing that it's true, right? And then over here, dealing with factorials at all can be very daunting, especially if this is your first experience. So sometimes, going back to your earlier limit approaches can be really helpful. So let's try the squeeze theorem on these two, right? So -5 sine n over n. What I'm going to do is I'm going to start with the fact that for any value of n, sine of n is going to be in between 1 and -1, right? This is going to always be true, just from the nature of sine of n itself. Okay, then on this inequality right here, I'm going to multiply everything by -5 over n. -5 over n and -5 over n. I want to point out that n is always going to be a positive integer here. Since we have an n in the denominator by itself, I won't even be doing a sub 0. It's going to be a sub 1, a sub 2. N is going to always be a positive integer. So this is going to always be a negative value that I'm multiplying here on these, which is going to reverse my inequalities, of course. But it's not going to do anything else. So I've got 5 over n greater than or equal to -5 sine of n all over n greater than or equal to -5 over n. So then at this point, I'm just going to use the squeeze theorem by applying the limit to each of these. So then I will have the limit as n goes to infinity of 5 over n is going to be greater than or equal to the limit as n goes to infinity of -5 sine of n over n, which is going to be greater than or equal to the limit as n goes to infinity of -5 over n. Okay, now of course, the guy in the middle right here is the thing that we're trying to figure out the value for. And if I'm going to be using the squeeze theorem, the piece that I have on either side had better be approaching the same limiting value so that they can squeeze the limit that we're looking for into the correct value. Well, the limit as n goes to infinity of just 1 over n, right, is 0, and it's times 5. So obviously this is going to be 0. And of course, for the same reason, this limit right here is going to be 0, which is 0 times -5. So what we're seeing is that our limit is less than and greater than these two things that are going to 0, and it's just going to get sandwiched together into that value, right? So overall, the limit as n goes to infinity of -5 sine of n over n is going to be 0. Right? Okay. Now, the b sub n over here. N factorial over n to the n. The first thing I need you to notice is that no matter which value of n you pick, there's going to be the same number of terms in the numerator and the denominator, because n factorial is going to count n, n minus 1, n minus 2, all the way down to 1. So that means there's n total things being multiplied. And then n to the n, I literally have n number of object n being multiplied. So both the top and the bottom have n number of objects, which I can then split up into separate fractions, right? So this is what I'm getting at right here. This is going to be n, n minus 1, n minus 2, 2 times 1, right? And in the denominator, this is literally n times n times n times n times n. Okay? So the next thing I need you to see is that I've got independent little fractions here, right? I'm going to split this into n over n times n minus 1 over n times n minus 2 over n times all the way down to 3 over n times 2 over n times 1 over n. Okay? So, if I were to look at each individual of these fractions, all of them except for the first one is going to be less than 1, where the first one here is actually equal to 1. Okay? And I know that it's going to be less than 1 because this is n minus 1 over n, n minus 2 over n. For example, this is like 4/5 and 3/5, and then on down and on down, right? The number on top here is always smaller than the number on the bottom. And it's the same thing for every one of these fractions all the way down. So especially if you pick an n that's large, which we're eventually going to do, because we're talking about the limit as n goes to infinity. Okay? So here's what I'm getting at. N factorial over n to the n is going to be less than or equal to 1 times 1 times 1 times 1 times 1 times 1 over n. Let's look at this for a second. What am I really saying? Obviously, this is equal to 1, right? Right here. But then as soon as you get to all of these other ones, as we were just saying, this little piece right here is less than 1. This piece right here is less than 1. So if I replace it with 1 each time, okay, then potentially this multiplication would be larger than the original, which is this thing. Okay? So then what I'm really saying is n factorial over n to the n is going to be less than 1 over n. Okay? And I mean, we can throw the equal to in there. I'm not trying to be 100% awesome proof here. You can go either way. But if you pick n large enough, past 3, 4, 5, the equal to is not going to come into play. Okay? So it's definitely less than this 1 over n here. Okay? And if we let n be 1, right? I'll have 1 factorial over 1 to the 1, right? Okay? Then I have that's equal to 1. And then from there, it's going to continue to be positive. So I can guarantee that this is definitely greater than or equal to 0, right? This thing right here is always positive, so I can guarantee that it's going to be greater than 0, okay? Now, with this right here in mind, I can go ahead and start to apply my squeeze theorem. I'm going to take my limit as n goes to infinity of 0, my limit as n goes to infinity of n factorial over n to the n, and my limit as n goes to infinity of 1 over n. And just as before, coincidence that it's 0, we actually get 0 quite a lot as a sequence limit, but not always. Obviously this one is 0 because the limit of a constant is itself. Here, we've already discussed this, and till you blew in the face, the denominator's overtaking the numerator quite a lot, right? That one's going to 0 also. Okay? So by the squeeze theorem, we can say that since this is in between those two, that the limit as n goes to infinity of n factorial over n to the n is 0. Okay, so this is just another approach that we can use for some of the more obscure sequences that we have. And like I said, this is by no means meant to be a huge, big proof here. I'm just trying to give you a good idea of a way to approach these things. Just as long as you can construct some sort of upper and lower boundary there and sandwich the thing in between two of the things that are going to give the same limit, then the squeeze theorem will work for you, right? Let's start to bring all of this together. What we're really interested in here when we're talking about sequences is we would really like to know if the sequence, an infinite sequence, is what we call convergent. And we've probably, we've talked about that word before, and you've probably seen it in a few different places. But convergent and divergent here have very specific meanings. For a sequence to be convergent, it means that the sequence has a limit at as n goes to infinity, right? As n increases without bound, there is an actual limiting value, a finite number that the sequence approaches and basically becomes as n goes to infinity. Okay? If there is not such a limit, like if it goes to infinity, negative infinity, or if the limit itself is just undefined, then that sequence is considered divergent. Okay? So convergent is what we're interested in finding. We are very interested in convergent sequences. Those we can build on top of later on and talk about convergent series that we're going to be doing in the next section. Okay? Some other little side terminologies here are bounded and monotonic sequences. Bounded is exactly what it sounds like. If you have all of your sequence terms and you can show that every term is between a high and a low, right? Every single term in the sequence is not above a certain maximum and not below a certain minimum, then you have a bounded sequence, okay? Monotonic means that you have basically a sequence that doesn't change direction, okay? Sequences that go increasing, then decreasing, then increasing, then decreasing are not monotonic, okay? Something is monotonic when it can just increase or just decrease for the important tail end. Now, it doesn't have to be the entire sequence. There are some sequences that they'll dip up and then come down, and for the downward portion, they'll be always decreasing for the rest. So there may have been an upward dip, right? But then after that peak, okay, you'll have a sequence that will decrease forever after that. So it would be monotonic after that peak moment, right? Or it can be monotonic for the whole stretch of the sequence, Okay, if you have a sequence that never changes direction, it never turns away from what it is already doing, like if it's always increasing or always decreasing for the entire sequence, that's fine too. That's monotonic. Okay, mono meaning one, right? And it has the feeling that you should be getting from this is that it's one directional. Okay, and it's not just about one little piece of it. It's about if you can find some finite number where everything before it didn't matter, but everything after, the infinite tail of a sequence, is all in one direction, just increasing or just decreasing on the infinite portion. Then you consider that sequence, or at the very least, that section of the sequence, monotonic. Okay? Now, if you have a sequence that is both bounded and monotonic, you're guaranteed that that sequence will be convergent. Okay? Now, through all the stuff that we've been talking about, I'm hoping that you're seeing that determining if a sequence is convergent is as easy as just doing a limit. Yes. But you also need to recognize some of the things that can make a sequence non-convergent. Even if you can find the limit and then show that the limit doesn't exist, sometimes the language is needed in order for you to convey why is it not convergent or why is it convergent. So what I want to do is talk about a few of these sequences here and show you why two of them are divergent and why another one is convergent. Okay? So here we go. Just by doing the limits straight out the bat, we can see which ones are convergent and which ones are divergent. Let's take a quick look at the limits here, right? The limit as n goes to infinity of n plus 3 over 2n is 1/2. Okay, so as you can see, right, using our little terminologies of the infinite top and bottom, you want to invoke L'Hopital's rule. That's a bit strong, or you can do the whole trick where you divide everything by n. That's fine too. One way or another, you should realize the limit of this being 1/2 means this is a convergent sequence. It does converge to some finite number as n goes to infinity, right? Next, c sub n here is 8 plus cosine of pi n. Now don't forget, we had another way of rewriting that, right? You can simplify cosine of pi n specifically because it's going to be whole numbers, right? Just because n is integers. N is not a continuous variable. So the fact that I can do 1 pi, 2 pi, 3 pi, 4 pi only means that this cosine is only going to be giving me -1, +1, -1, +1. Okay? And then we talked about the limit of this, right? The limit of this doesn't exist. 8 plus -1 to the n is undefined. So we would consider that sequence divergent. And then this guy here. No simplification necessary. Limit as n goes to infinity of 5 minus e to the n. The limit of the 5 is just 5, but then I have minus the limit as n goes to infinity of any exponential with a positive exponent like that is going to be infinity. 5 minus infinity is going to give me -infinity as my result here, right? So this is divergent sequence, and so is this one. Okay? Let's talk for a minute about why those two are divergent. This one, the bottom one here, should be blatantly obvious. It is not bounded, right? There is no boundary on the underneath of this sequence. It has an upper boundary, right? When n is 0, I have 5 minus e to the 0. 5 minus 1 is 4. So that has an upper boundary of 4. But as you can see, as n goes to infinity, the sequence itself plummets to -infinity. It is unbounded. Okay? So unbounded. underneath. It has no lower boundary. Therefore, it can't converge. It converge literally means to focus in on a value. And if you're, decreasing without boundary and just taking off, it's not focusing on anything. It's leaving the entire universe, right? So unbounded is definitely a way to immediately get a divergent sequence. Okay, no, but this one right here, this one is bounded. Plug in a few terms and see what you get. Look, C0, right? When negative 1 to the 0 is 1, I get 8 plus 1 is 9. C1 is 8 and then minus 1, so 7. Right? C2, I'm back at 9 again because this being an even power, I get 8 plus 1 again. Then C3, I get 7 again. So what I'm getting here on this graph is a sequence that every time I move along the n axis, it's going 7, 9, 7, 9, 7, 9, 7, 9. It's completely bounded, right? This is bounded between the values of 9 and 7. So we got the bounded part, but it's not monotonic. It's constantly going up to 9, down to 7, up to 9, down to 7, forever. It is never picking a direction. It is never focusing in on any particular value. It's just going to keep bouncing back and forth between those two. So since it's not monotonic after a certain point, it can't converge. Therefore, a divergent sequence. Okay, so now this one. We've already shown that by this definition of convergent, there is a limit. So this is a convergent sequence. Therefore, I should be able to show that it is both bounded and monotonic, right? I want to take a look at the monotonic part especially, because that's not something we're accustomed to showing, and I want to show you a couple of good ways to do that. First, let's talk about bounded though, okay? I can see that if I plug in a sub 0, right? Let's do A0. Then, not A0, I'm sorry. Can't do 0, 1. A1, I'm getting 4 over 2, which is 2. Right? A2, if I plug in 2, I have 5 over 4. A3 is going to be 6 over 6. Ironically, it's 1, right? And then let's do one more. A4, 7 over 8. So I hope you're noticing that at every step, this thing keeps decreasing. Now, this by no means is a proof that it's monotonic, but it should start giving you an idea that it probably is. Okay? The limiting value is 1/2. 7/8, right, is where I'm at the fourth term. It's going to continue to decrease to the 1/2. We can see that it's bounded, even if you don't include the 1/2, because maybe, if you don't know about the limit part yet. Let's say you don't know about the limit part. It's still bounded, right? These values keep going down. I have an upper boundary of 2, and I've got a lower boundary of 0. These things are always going to be positive. I'm plugging in positive integers only, 1, 2, 3, 4, 5. And this is addition and multiplication. They're going to stay positive. So if nothing else, I've got a lower boundary of 0. And then I've got this upper boundary of 2, unless this thing, spikes upward. Okay? So to complete the idea that this is bounded by 2, that it never, turns back up, let's switch gears and show that it is monotonic. Okay, if it's monotonic, like you can see this is decreasing, if I can show that it's always decreasing, then 2 is definitely the upper boundary because it's leaving 2 and it never turns around. So let's do that. To show that something's monotonic, there's a couple of different ways. The straightforward way for monotonic is to show that for any term, a sub n is less than a sub n minus 1. Okay? Now, of course, I say monotonic, I should say monotonic decreasing. Okay? What if I was going to show monotonic increasing? I would put a greater than here. Okay? If there was a greater than here, it would be monotonic increasing. What I'm basically saying is if you pick any term, a sub n is generic. I'm saying that that term is going to be less than the previous term, n minus 1 term. Right? That's what this is saying. If this is true for all values of n, okay, or maybe you can show for all values of n past a certain number. So sometimes it works for all n, and sometimes it's like, okay, 6 and on, it works great. Okay, so this is where I'm going to start with. I suspect that this is monotonic decreasing. In other words, decreasing and never switching back to increasing. So that's why I've set this up. If you were going to do monotonic increasing, you would just change this to a greater than to show that each term is greater as it goes. Right? So then, a sub n is n plus 3 over 2n. A sub n minus 1 is n minus 1 plus 3 over 2 times n minus 1. And then from here, I just need to solve the inequality and see if it's true for some n, all n, or just a portion of the n that I'm interested in. Okay? So then from here, I'll just simplify a little bit. And I will note the n's here are all positives, and I'm going to make the assumption that they're bigger than 1 because we're talking about further down the line. Okay? We're going to assume that I'm not going to get 0 in this denominator here. What I'm going to do is I'm going to multiply the pieces here. So I have 2 times n minus 1 times n plus 3, right? I'm multiplying this piece here. I'm multiplying both sides by 2 n minus 1 is less than, and I'm going to multiply 2n to both sides here too. So I'm going to get 2n times n minus 1. Oh, well, that's basically just n plus 2. Roger that. Because n minus 1 plus 3 is just n plus 2, and I'm multiplying 2n over to that. And I'm sticking with less than because, remember, we're saying that n is not going to be any negatives. Okay? And we're not switching any sizes here, so it's not going to flip the direction of my inequality. Okay, so then I have 2n squared. Then I've got 3n, 2n times 2 is 4n. And then I've got negative 3 times 2 is negative 6. Less than 2n squared plus 4n. So I can subtract the 2n squared from both sides. Okay? And then I'm going to subtract the 4n from both sides. And that leaves me with negative 6 is less than 0, which is always true. So what this is telling me is that this is always true. Therefore, every time I pick any term, it's going to be less than the term that came before it. In other words, monotonic decreasing. For the entire sequence in this case. The entire sequence is going to be decreasing. So that's one way that you can show this. You set up the current term and the previous term, and then you just show how the inequality works. And make sure, if you're really doing this as a real proof and not just hand waving a little bit like I'm doing, that you actually write down the details, right? The details such as n is a positive integer bigger than 1, so we don't get this division by 0, and so on and so on. the little bitty nitpicky things. Another way to show that something is monotonic is to use that same little trick we used earlier for L'Hopital's rule, and that is to bridge it to a function. Okay? So imagine that I have some function f of x plus 3 over 2x. If I've got a continuous function, then I can take a derivative. And the derivative tells me regions of where something is increasing or decreasing. So the technique here is go back to Calc 1 and look at some of your curve sketching techniques where we would do that first derivative sketch with the number line sections. Basically, I'm going to use what we call the first derivative test to find the sections of increase and decrease, and then that will tell me right away where this list of numbers changes direction. Okay? And the reason why I can do this is because the continuous function has the sequence inside of it. Okay? And then if the function ever changes direction, the sequence may or may not, but if the function doesn't change direction, then the sequence absolutely can't either. So then let's do that. I'm going to take my derivative here, f prime of x. Using the quotient rule, I'm going to have low d high, so that's 2x times 1, minus high d low, so 2 times x plus 3, divided by low squared, so that's 4x squared. My derivative, f prime of x, is then equal to, I have 2x minus 2x, so those are going to add up to 0, and then I have negative 6 over 4x squared, which I can then reduce to negative 3 over 2x squared. Well, this is a nice one right here. I actually don't have to do the little chart, but if you doubt it, then go ahead. The only thing that's going to separate this chart, the only critical point I've got, is where x is 0. Notice the derivative will be undefined when x is 0. So if I were doing the little first derivative chart, I would only put 0 on the x-axis. And then I would just pick a couple of points on either side, right? So over here, like f prime of negative 1, let's say. F prime of negative 1, negative 1 squared is 1. I'm getting negative 3 halves. The derivative is negative. This is decreasing. I actually don't care about this section though. This is the interval of numbers from negative infinity to 0. And don't forget, n can only be positive here. So actually, this is the section that I'm concerned with over here. What is f prime of positive 1? If I plug in positive 1, I get the same value. I get negative 3 over 2. Which, since the derivative is negative, I get decreasing. So again, this is showing us what we already looked at on the last version. Every value greater than 0, which is what n is. N is any whole number greater than 0. All of your directions are going to be decreasing. Okay? So whether you like to do it with inequalities or if you want to use a parallel with a function, of course, the only time that this is going to really fail to show monotonic is if you can't do the function, like with a factorial or something like that. But other than that, you can use the derivative as a quick method to get there, or you can do the inequality. And that's if you really have to show something is monotonic. I'm just really digging in deep here. We already knew that this one converged because we see the limit. And that's actually 99% of the time. You're just going to approach a sequence, take the limit, it converges or it doesn't converge, right? You either get a limit or you don't. Sometimes it helps to know some of the background pieces though. Why doesn't it converge? Oh, that one's alternating, right? It just alternates between the same two numbers over and over again. Not all alternating sequences do that. Some alternating sequences grow away from each other. As they alternate positive and negative, they get unbounded. Other alternating sequences alternate between each other, and it gets smaller and smaller, like they do this. Okay, so just because it's alternating is not what did this. The fact that it's alternating and it never, hones in on it. Let's get a couple of more examples and then call it a day. So let's finish up with some examples, just to, sort of have a all-in-one idea here, right? 3/5 to the n. Now, some of these you may recognize from earlier in the lecture here, and some of them are a little bit altered, and some of them are completely different. So the first thing that you'll want to do is, if you can, recognize the type. Hopefully you've recognized this one now as a geometric sequence. Geometric sequences either converge to 0 or they diverge. And it has to do with the size inside of the rate there. So start with a limit. The limit as n goes to infinity of 3/5 to the n. Since 3/5 is less in size than 1, this is going to be 0, which means this converges. So the idea here is, if it had been, say, 5/3, right, then this thing would continue to increase without boundary. But since it's 3/5, 3/5 is less than 1, the more you multiply, the smaller the value is going to get, because you're multiplying by something less than 1 over and over and over again. Next, this is an alternating sequence. I've got the -1 to the n here. We're just going to make every other term negative, right? So positive, negative, so on and so on. I'm really going to start with just the limit of the inner piece, because I don't really do the limit of the alternating, right? The limit of the negative positive doesn't really have a definition, but I can get a limit of the main body here, and that's going to tell me something about the size of the sequence. Okay, so that's what I'm going to be concerned with at first here. So I'm going to start with this limit as n goes to infinity of 4 to the n over 2n plus 1. Okay, now I've got a combination there of exponential and linear. So I'm going to bridge over to continuous variable x. Limit as x goes to infinity of 4 to the x over 2x plus 1, with the sole purpose and my goal of using L'Hopital's rule here. So then this is going to be equal to the limit as x goes to infinity of taking the derivative here, because I've got infinity over infinity. That's going to give me ln of 4 times 4 to the x over 2. Okay, now of course these are numbers unaffected by the limit, and the limit as x goes to infinity of the 4 to the x, of course, is unbounded, infinite. So therefore, this sequence b sub n is divergent. Notice I didn't even have to address the fact that it's alternating. Okay, the alternating didn't do anything. This particular one, the size is growing. So even though it's alternating, it's going, it's going to start small, and then the alternating is just going to keep getting larger and larger, and it's just going to diverge. It's going to peel away. Okay, next, -8 e to the 2n plus 1 over 1 minus n squared. Well, I'm going to focus on the main meat right here, which is just in the exponent. I'm going to start with that limit. The limit as n goes to infinity of just 2n plus 1 over 1 minus n squared. Notice I've got n squared on the bottom and n to the 1 on top. Using our quick little rules of infinite limits here, since the bottom is more powerful than the top, I already know that this limit is going to 0. If you need to do the steps, just remember what you're going to do is divide everything by n or n squared, which is depending on which way you want to go. And if you divide that out, you'll see that everything is going to 0 out in the numerator, and you'll get 0 for the whole thing. So what does this mean? It means as n goes to infinity, what I'm going to get is that the limit as n goes to infinity of c sub n, the whole thing, is going to be negative 8e to the 0. Because this piece is going to 0 as n goes to infinity. So the limit of my sequence is going to be negative 8e to the 0. E to the 0 is just 1 times negative 8 is negative 8. I found a finite number that this limit exists in, and it's the limit of the sequence itself. So this sequence is convergent. Okay? S sub n is n times the ln of 1 over n. This limit, we can just employ some of our natural knowledge of logarithms and n itself. First and foremost, I can say that this is n times the ln of n to the negative 1, because that's what 1 over n is. And I'm going to use my logarithm rule here to take the negative 1 out. So S sub n is equal to negative n times the ln of n. All right, so it's an open and shut limit on this one. The limit as n goes to infinity of S sub n is going to be negative infinity times infinity. So just negative infinity. So this one diverges. Because it's unbounded. It's actually really unbounded. As n gets large, even if you go with the original one here, as n gets large, 1 over n is going to approach 0. And ln of approaching 0 is negative infinity. And then n, of course, is getting large to infinity. You have infinity times negative infinity. Either way, this is what you're going to end up with. It's going to diverge. Okay, n times sine of 1 over n. I'm going to use a calculus 1 technique here. I'm going to rewrite n as over 1 over n, like this. And then I'm going to do the limit. The limit as n goes to infinity of sine 1 over n over 1 over n. Okay? Now, side note, don't forget, as n goes to infinity, 1 over n goes to 0. So this is going to be the same result as if I were to take something like the limit of, I'll just use a little a. I know I've used it already over there, but let's say a goes to 0 of sine a over a. This is essentially the same idea, because as n goes to infinity, both of these are going to 0 simultaneously as the same value. And I'm hoping that you recognize this limit from calculus 1 to equal 1. So this one converges. Okay? Here's another alternating series right here. So I need to be on the lookout, especially those alternating ones, the way they bounce back and forth. They can sometimes be bounded, sometimes they can be unbounded, sometimes they can still be divergent even if they're bounded. This one, I'm going to focus on, just like before, right, whenever we have the alternating, I focus on the main meat of the sequence, not the alternating portion. So I'm going to take the limit as n goes to infinity of 1 over the square root of n squared plus 5. Okay, this is an obvious limit. The numerator is a constant. The denominator is going to infinity. This is essentially the same as the limit as n goes to infinity of just 1 over n, essentially. Whatever techniques you want to do, divide by n squared here and let it trickle up to the top, whatever. This limit is going to 0. Okay? Now, it's alternating. So what's happening is this sequence is starting out far apart, and then it's bouncing back and forth. It's alternating. But every time it goes back and forth, it gets just a little bit closer to 0. The size is shrinking to 0. The alternating has nothing to do with this process. The size of all of the terms keeps decreasing with a limit of 0. So the sequence is going to do this. It's going to converge to 0. The overall limit of the whole thing, alternating in all, of just d sub n here, is 0. Because it's basically negative times 0, positive times 0, negative times 0, right? It's going to be all 0. So this one converges. Next, I have another alternating series here. Not series, sequence, sorry. Another alternating sequence here. So again, I'm going to focus on the main body. And I'm going to do that first and foremost by rewriting it. The first thing I'm going to do is I'm going to divide everything by 3 to the n. Okay? So I'm going to take this portion right here, and I'm going to do 3 to the n divided by 3 to the n over 3 to the n plus 1 divided by 3 to the n minus 2 over 3 to the n. And I'm going to simplify this. I'm going to have 1 in the top, and then I'm going to have 3 right here minus 2 over 3 to the n. Now, bear with me on that one, right? Make sure you're with me. 3 to the n plus 1 divided by 3 to the n. Since they're the same base, you subtract the powers. N plus 1 minus n is just 1. So I have 3. Take the limit of this as n goes to infinity. So that's what I'm doing here. Take the limit as n goes to infinity of this. In other words, this is the same as that body. I just rewrote it. I'm taking the limit as n goes to infinity of the main portion of the sequence. Okay, so what do I get? The limit as n goes to infinity of this is going to be 1/3. Because as n goes to infinity, I have 2 over infinity. This piece is going to go to 0. And I'm left with 1 over 3 because there's no other n's in there. Okay, so it converges, right? Nope. We didn't finish talking about one little piece. The fact that it's alternating. Okay? So the limit here of the body portion is 1/3. But if you try to take the limit of the whole thing, it's alternating. 1/3, negative 1/3. 1/3, negative 1/3. Okay? This sequence is trapped between, as n goes to infinity, okay? The sequence alternates between 1/3 and negative 1/3, okay? It's going to keep going back and forth because the size of the thing traps at 1/3. That's what the limit is telling you. The limit is saying, hey, the size of this thing is going to stay at 1/3. But then every single term keeps changing back and forth. 1/3, negative 1/3, 1/3, negative 1/3. So it starts out a little different, and then it hones in on 1/3 and negative 1/3 and just stays there, right? It keeps bouncing back and forth between these two values. Or, well, it's, gets close at first, and then as you get to infinity, you're pretty much right on top of 1/3 and negative 1/3. But it never picks one to be the final value. You can't get to a final value here. Okay? So, this is not monotonic. It is bounded, not monotonic. This one diverges. Alrighty? Last one. I just need to perform that limit. The limit as n goes to infinity of n minus the square root of n squared plus 1. The technique here is to multiply the numerator and denominator by n plus the square root of n squared plus 1. Like so. And then we'll see what we get. So I've got my limit as n goes to infinity. I'll have n squared in the numerator. I'll have minus n square root of n squared plus 1 plus n square root of n squared plus 1. That's these cross terms, the outer and the inner there. And then the last two are the same square root, and there's a minus. So I've got minus n squared plus 1, like that, right? Negative times positive is negative. And then square root, square root. I would technically have an absolute value there, but n is guaranteed positive, plus it's squared. And then my denominator is simply 1 times this thing, so I'm just going to get that thing. These are going to add out to 0, and I have n squared minus n squared. So I have this limit as n goes to infinity of negative 1 over n plus the square root of n squared plus 1. Okay, so now that we've gone through all of the algebraic manipulation, now let's take a look at what the limit is doing. As n goes to infinity, I'm basically getting infinity plus infinity-ish, in the denominator. And so I've got a constant over infinity. This limit is going to go to 0. So this one converges. So I hope this lecture has helped you understand what a sequence is and what our goal is in evaluating a sequence. Next up, we're going to show how sequences build into series, and then through the whole unit, we're eventually going to show how series helps us understand functions a whole lot better than we did before.
So let's get a few more visuals, because sometimes you'll be given sequences as graphs, and you'll have to determine from the graph itself if they're converging or not. Let's start with the one from 2 scenes ago, where it was n plus 3 over 2 times n. This is the function x plus 3 over 2x, the one that's completely continuous. And of course the sequence is going to fit along the curve, but only at the whole numbers there. And as you can see, just like the curve, this thing wants to approach a value here. In order to really see that value, I'm going to increase the stretch here to 0.5. You can see 0.5 is right here. And I'm going to bring in the n values. So you can definitely see that this sequence is actually approaching the 1/2 point right there. And it is bounded and monotonic. It never changes direction. Next, let's take a look at the geometric series 3/5 raised to the x. So that'll be number 2. Alright, so here's the graph, and I'm not always going to be able to show the graph. GeoGebra doesn't handle some of these as well as it could, but it handles this one pretty well. It's just a normal exponential, and of course there's your sequence starting with the n equals 1 there, and you can see, just like any exponential would be expected to, it very quickly attains its goal, and it starts hugging the 0 line here. And that's the actual sequence right there. Okay, next we're going to talk about the divergent series, -1 to the n times 4 to the n over 2n plus 1. GeoGebra is not going to graph the constant curve because of the -1 to the x is not a very easy thing to graph continuously. The sequence, however, it will graph. You can see there's a couple of the points right there, and I'll need to shrink this size down a good bit. See, we've already got a few pieces here, and I'm going to have to continue to shrink this down so that you can see what's happening here. Is it is alternating. You can see you have one below, one above, one below, one above, but the further we go down the line, the larger the distance becomes, which is why I keep having to shrink this down. See, we're already in the thousands here. This thing is definitely diverging. These dots are taking off in distance, very, very far away from the center there. Okay, next we're going to look at -8e to the 2n plus 1 over 1 minus n squared. That's this guy right here. As you can see, the function itself has this downward trend right here, and it's monotonic once it gets past this point in between 1 and 2 there. Okay, so then I'm going to look at just the sequence here. I'm going to squish it in really far. So you can see that these are the sequence values, and they're definitely going in a decreasing fashion. They're definitely monotonic, and they're definitely honing in on the -8 number there. You can see that -8 would be the limiting value, sort of like an asymptote there. Okay, next we have the n times ln of 1 over n. And this is what the graph itself would tend to look like. And remember, this was going to -infinity. So I'm going to really shrink up this y-axis here so that you can see exactly the trend. And here's the actual sequence. You can tell right away this thing is taking off to -infinity. It's going down really, really fast. Alright, next we have the x n times sine of 1 over n, which will be number 6 here. Okay, so then the graph itself has a very intriguing shape towards the center there, and that's actually not the part we're interested in, because we're not allowed to have anything less than 1 for our value anyway. So as you can see, here's our sequence, and it almost immediately starts hugging the limiting value of 1 there. It's definitely squishing itself up to be nothing but the value of 1. Okay, the alternating series, -1 to the n divided by the square root of n squared plus 5. That's the 7th function here. Again, this one, it won't graph it because GeoGebra doesn't handle the continuous version of the -1 to the x, but you can see, I'm going to spread it out here, and it's actually not very large numbers themselves for the sequences, but you can see it's an alternating series. Number 1 is up here, or I'm sorry, number 1 is down here, number 2, then 3, 4, 5, 6, 7. It keeps alternating here, and it keeps getting closer and closer and closer and closer, and until finally, if you ever could get to infinity, this thing would actually be on top of 0. So this one does actually converge to 0, as you can see. It sits here and alternates between these two. You can't really see the alternating, you have to imagine it bouncing from dot to dot here. Okay. Next, we have the alternating series, negative 1 to the n, 3 to the n over 3 to the n plus 1 minus 2, which is the one that we said the limit converges, but the sequence itself does not, because the size gets small enough, but it never actually makes up its mind between a negative and positive 1/3. And it's actually what you can see exactly what's happening here. It starts off a little bit off on each end, and it's going to alternate here between these two. It's going to hone in on negative and positive 1/3 the whole way, and it's never going to deviate from these two after you get far enough down. It's going to be constantly on the 1/3 mark and negative 1/3 mark, and it's never going to be anything else. Okay, and then lastly, n minus square root of n squared plus 1. Change this to a 9. And again, this is one of those ones that you can see very quickly that it converges to its limiting value. It will graph the curve itself on this one. You can see there's the curve. Here's the sequence though. It very quickly gets close to 0 as the numbers become very large. And here's how the sequence goes. It does actually get up to 0 close enough there.